Hi, welcome to the final week of the NPTEL course on information theory. In the previous week, we saw the definition of channel capacity, and we stated Shannon's channel capacity theorem, channel coding theorem, which claims that the maximum number of bits that one can send in an error-free manner asymptotically per channel use is given by this quantity called channel capacity of the channel W, and it is given by, this is the result, this formula, maximum over all input distribution Px, the mutual information between the input X and the output Y obtained by passing X through the channel. So X is generated from this Px distribution and you pass it through the channel and you see a Y. The mutual information between this X and Y, if you maximize that mutual information over all input distribution, that's channel capacity. So this result, channel capacity, was defined operationally, and this is a characterization of channel capacity. So this result is called Shannon's channel coding theorem. And we have been we have been trying to prove this over the last week. One thing we saw was that it's easy to see how this works for binary symmetric channel. So for binary symmetric channel with flip over probability delta, this channel capacity CW is given by 1 minus H delta, where H is the binary entropy. So this H is delta log 1 by delta plus 1 minus delta log 1 by 1 minus delta. And we saw how we can get a lower bound for channel capacity using the sphere packing bound, showing the inequality in this direction. Sorry, we get a converse result by showing sphere packing bound, showing the inequality in this direction. And then we gave a scheme using a randomized construction, and that gives inequality in the other direction. That's how we proved this thing for binary symmetric channel. A similar proof was given for a general channel, where we showed a single shot result. We showed that suppose for an input distribution X, and let Y be the corresponding output. Suppose you can show that the pair of XY that have larger probability under XY as compared to PXPY, probability larger than 2 to the power lambda, so log likelihood ratio greater than lambda. Suppose this guy has probability, this is a proof we saw for general W. Suppose this guy has probability greater than 1 minus epsilon, then we saw that we can send roughly 2 to the power lambda messages over W with probability of error with average probability of error less than epsilon. Okay, that's what we saw. And this was a single shot result, in the sense that doesn't speak about multiple channel uses, but we apply this result to the case when we use the same channel W multiple times. So we replace W with Wn and choose Px to be an independent distribution. So this Pxy, the resulting Pxy becomes a product distribution. And for product distribution, this bound is just a large probability lower bound on sum of independent random variables, and so it's the expected value of this guy. So the right choice of lambda is n times the expected value of individual guys, which is the divergence between this joint distribution and product of marginals, which is the same as mutual information. So from that, what we obtained last time was that the number of messages that you can send per channel use is asymptotically 2 to the power n ixy roughly. So the capacity exceeds this for every input distribution Px. Note that this proof, the way we did this proof, this part of the proof is called achievability proof. The way we did this proof, we constructed randomized codebook generating with coordinates generated independently using the same distribution px. So each coordinate was generated independently from px, and they were generated that way. And then we saw that this randomly generated codebook has small average probability. Therefore, there must be one realization of x1 to xn of code words of length n, for which the average probability is small. Alternatively, if you have physically available ways of implementing randomized codebook, then thus this randomized procedure itself can be used. And in fact, we can show that most of the code words generated this way will work, and therefore you might as well just use the randomly generated codebook as a valid code word. That's also done in practice. But for the purpose of this course, where we are not focusing on the code design aspect but just showing that such codes exist, it is important to note the role played by this input distribution. For us, it was used as a tool to discover codes of optimal length. The code words as such were deterministic, and there was no distribution on the code words. Okay, that's for our proof. Okay, so there's a technical reason why we have input distribution. And this single letter, this expression which we get finally can be thought of as sometimes called a single letter expression. It doesn't have that n because we have already taken limits over n. So we got this single letter lower bound on the capacity. Okay, so the upshot till now is that capacity is maximum mutual information over all input distributions, and we have already shown the existence of a scheme that achieves capacity. In the next lecture, in the first lecture for this week, we will show that no scheme, no matter what you do, no scheme can beat this optimal rate max over px ixy. This is called the converse part, which will complete the proof of Shannon's channel capacity theorem, channel coding theorem. And after that, in the final unit for this course, we will look at not a discrete. So till now we have been looking at a discrete input, discrete output channel. We will look at a continuous input, continuous output channel, namely the additive wide Gaussian noise channel. Okay, so see you in the next lecture.